Imagine a ledger with two columns, debits and credits. Every entry you add must keep the ledger balanced. The sum of debits equals the sum of credits. If a single transaction breaks that equality, something is wrong. Maybe an entry was omitted, or a sign was flipped, or a conversion failed. That balance is an example of a semantic invariant. It's a property about your data that should always be true if the data means what you think it means, not a formatting rule, not a guideline, a rule that, when violated, signals a semantic problem. Semantic invariants are the simple, stable truths you rely on to know that your data still carries the intended meaning. Let's make this precise. A semantic invariant is a statement about data, often a relationship or constraint across fields or records that must hold whenever the data accurately represents the underlying reality. It's not about how data is stored, it's about what the data says about the world. Here are a few short, concrete examples. Accounting balance means the total debits must always equal the total credits. Referential integrity means that every order must reference a user that actually exists in the users table. Conservation means inventory follows a simple rule. The total inventory at the next time step equals the current inventory plus receipts minus shipments. Monotonic timestamps mean an event's creation time must always come before the time it was processed. Uniqueness means each transaction ID appears only once and is never reused. Sum consistency means the invoice total must equal the sum of all its line item amounts. Each of these expresses an expectation about the meaning of the data. When any of them fail, the failure is semantic. The data no longer reliably maps to the real-world fact it's supposed to represent. Why are invariants useful? 3 reasons stand out. First, detection. Invariants turn invisible semantic errors into visible signals. A simple equality check can flag a missing join, a unit mismatch, or a pipeline bug long before it reaches reports or models. Second, documentation. Writing an invariant is a compact way to state what you expect the data to represent. Invoices must sum to their line items is both a test and a human-readable contract. Third, resilience. Systems that monitor invariants detect change early. When invariants break, you can stop downstream processes, trigger investigations, or apply guarded fallbacks. Not all invariants are the same. Let's categorize a few types. Local invariants apply to a single row or record. Cross-record invariants relate multiple rows or tables. Example, referential integrity or uniqueness across a dataset. Global invariants apply across an entire dataset or time window. Example, total inventory conservation over a day. Statistical invariants, distributional expectations, like less than 1% nulls in this column. These are soft but useful guards. Temporal invariants, expectations about stability over time. For example, a code set that shouldn't gain new categories without a coordinated change. Some invariants are strict and absolute. Others are probabilistic and monitored as signals rather than hard failures. How do you design useful invariants? Start with domain truth. Ask what relationships must hold if the data is correct. Talk to domain experts. Inspect sources and business rules. Convert those rules into clear statements. Prefer simple, testable rules. Instead of totals, should be roughly consistent. Write a clear tolerance rule if that tolerance makes sense. Make the tolerance explicit. That's part of the invariant. Capture invariants close to the data. Put them in schemas, data contracts, or validation layers in the pipeline. Machine readability is important. The system should be able to execute the invariant automatically. Next, enforcement and alerts. Decide whether an invariant is hard or soft. A hard invariant will reject or quarantine data when violated. Use this when a violation would produce catastrophic downstream consequences, for example, billing calculations. A soft invariant raises alerts but allows processing to continue. Use this for noisy signals or when temporary divergence is acceptable. When an invariant fails, include context in your alert. The failing rows, the pipeline version, the source system, and recent deployments. That context makes debugging faster. Also, keep a remediation path. For example, your alert might trigger an automated rollback of a deployment or route affected records to a manual review queue. A few practical patterns. Implement invariants as tests in CI. Before a pipeline change reaches production, run invariant checks on a staging dataset. Run lightweight, continuous checks in production. Many invariants are cheap: sums, counts, existence checks. Run them frequently. Monitor statistical invariants with thresholds and anomaly detection. Use historical windows to set baselines, but be careful about seasonality and expected change. Version invariants alongside schemas. If you change the meaning of a field, update the invariants and bump the schema version. Record violations and their resolutions. Over time, you'll build a knowledge base of why invariants broke and how they were fixed. That history improves future design. Beware of a couple of pitfalls. First, overly strict invariants can block legitimate change. If your business evolves, new product lines or new currencies, strictly enforced checks without change management will generate noise. Pair enforcement with clear change control. Second, fragile invariants tied to implementation details can be misleading. An invariant that assumes a specific column order or a particular encoding will break when engineering-level changes occur. Keep invariants tied to semantics, not incidental structure. Third, don't over-rely on invariants as the only safety net. They catch many problems but not all. Combine invariants with lineage, schema versioning, sampling, and human review. To sum up, semantic invariants are compact expressions of what your data must mean. They are tools for detection, documentation, and resilience. Well-chosen invariants reveal errors early, communicate intent clearly, and make systems easier to operate. Design invariants from domain truth. Make them testable and versioned. Decide when to fail hard and when to alert softly. And treat a broken invariant as a learning opportunity. Update documentation, fix the pipeline, or adjust the invariant if the world legitimately changed.